Hey, so we're at reInvent 22 in Las Vegas, and we're here with Karthik Raman. Karthik knows more about HPC application performance than almost most other people on the planet. So this is a good time to be able to talk. Now, this morning in Adam's keynote, he announced the Hpc6id, which is powered by Intel Xeons. Now these are Ice Lakes.
These are Intel Ice Lakes.
Intel Ice Lake processors. What else is interesting about them? Because, like, this is now the third HPC instance that we've announced.
That's right.
We had the Hpc6a with AMD, and we had the Hpc7G announced last night at Peter's Monday Night Live.
Yeah.
Using the AWS Graviton. That's our ARM-based processor, and then today we're talking about Hpc6id. Why did we need a third? Not apart from just making sure that that we had one of everything, which is good. But why did we engineer the 6id the way that we've done?
Yeah, sure. So let me start with what the specs are for Hpc6id. So as you rightly said, Boof, it is powered by Intel Ice Lake. It has 64 physical cores. Hyper-threading is disabled.
Yep.
And it has 1 terabyte of physical RAM.
That's a lot, right?
Yeah, that's a lot of RAM.
And especially for a 64-core node. What is that? How many gigabytes per core is that?
That comes to 16 gig per core.
16 gig per core.
That is right.
That is a crap load of memory per core.
That is correct.
Okay.
And then we have 15.2 terabyte of local NVMe disk as part of that. And we also have 200 gigabit of EFA networking that comes as part of that as well.
So it's a lot of, that's twice as much EFA as we've got.
That's correct.
Actually, that's twice as much EFA as we've got on the Hpc6a, the AMD machine.
Right.
Right. So twice as much EFA for fewer cores, but these are Intel cores, so they're generally higher performing floating. From a floating point of view, higher performing cores, right?
Correct. They actually support AVX512.
Yep.
So a lot of the codes, and I think a lot of these codes actually can benefit. And I'm going to talk about that a little bit more on what kind of codes actually are suited for HPC6.
Yeah, right.
So when we were talking to our customers, a lot of customers actually run finite element analysis and a lot of structural codes. And these structural codes are categorized into, they have different types of solvers. You have sparse direct solvers or iterative solvers. Iterative solvers typically do not need a lot of memory, but direct solvers actually do need a lot of memory. And when I say lot, like you have problem sizes which can run all the way to 5 terabyte of RAM, and for that you will scale across multiple nodes, obviously.
Yeah, right.
But even but a lot of these codes are not meant to scale to a very large node count. So they want to scale to a small number of node counts and fit as much as possible in the physical RAM.
Right. Okay. So that makes sense. Then, hence the need for a terabyte of RAM, small number of cores, and all the cores being really punchy.
That is correct. Yeah.
Right.
And in addition, they also have this capability to run in-core and out-of-core solvers. So what that means is, when you're running the solver in-core, you're basically putting majority of the data in the RAM, and you're doing all your matrix calculations out of the RAM. And when you run out of core, it kind of does a partial of that in RAM, and then it falls back to the local memory that you have. And that's why we also need the local NVMe, because when we are doing something like out of core, so say if you run a big problem size and you run out of core, you don't want it to actually fall back to a file system and be bottlenecked by some of the performance of the file system.
Right.
And then you need some faster disk. And that's why you actually have a large local NVMe volume as well.
Wow. Okay. And so that actually, you've basically just mapped it straight on there. So that totally explains why we need the NVMe.
Right.
So you're saying this is basically characteristic of most of the structures codes are in.
Correct. Yeah. So there are two main examples that I can take. One is ANSYS Mechanical.
Yep.
So ANSYS Mechanical, actually, we ran a series of benchmarks using the V22 version of Mechanical, and it had a bunch of iterative solvers and direct solvers. So iterative solvers stress more of the memory bandwidth, and the directive solvers actually stress more of the CPU flops.
Yep.
So we saw that the performance obviously had it kind of varied based on the type of solver you're running, but overall geomean across 6 of these benchmarks that we ran, we saw a 45% speed up over the prior generation Intel Cascade Lake based instance, which was the R5D and 24x large, which is what this these codes were typically running on earlier.
All right.
So
R5, hang on, say that again. An R5DN.
and 24x large, yeah.
Right. Oh, okay. That totally, okay, it makes sense.
Yeah.
So these are really jumped up R5DNs, or actually,
Yeah, that's true.
Okay, but
And
with
that is
newer
just
processors.
and that's just a performance, right? And if you look at the price performance, the price performance is even more competitive. So compared to the R5D, and if you just look at the on-demand pricing here, we were actually getting up to 2x performance over the prior generation, which is the R5DN on Hpc6id.
Right. And the R5DN would have only had 100 gigabits of
Correct.
networking,
It had
so
only
this is 200.
That is correct.
How many cores were in the R5s?
It was 48 physical cores,
Right.
and versus 64 now.
So more cores, newer cores, twice the network bandwidth,
Yeah.
and local, and of course, well, the D, I guess, you know, they already had NVMe attached.
That is correct. Yeah.
Okay, and so so we're getting like 2x better price performance.
Yeah.
What's the performance per node comparison like?
So the performance, so I mean the performance per node. So if you look at like some of these structural codes, like ANSYS Mechanical is one example that I took, which was or geomean across 6 benchmarks.
Yep.
Then there's another one called as Actran, and Actran is from Hexagon. It's an acoustic simulation software which is used by a lot of aerospace and defense industry for basically studying the acoustics of certain structures. So as an example, if you look at the aerospace, when you are flying in an airplane, you know that the turbofans actually generate a lot of noise, but they have to design the acoustic liners to minimize that noise. So that is where this particular application is used, and that also has a very similar characteristics wherein the performance, the memory requirement is pretty huge. So you kind of need over a terabyte of memory, and there we saw up to a 60% improvement in performance alone.
60%.
60% improvement over the R5DN, like the prior generation. Yeah.
Wow. So that's significant.
Yeah, it's
Boy, is that significant.
Yeah.
60% performance improvement. And of course, it's cheaper.
Yeah, and it's at 2.2x cheaper actually over.
This is like a one-question IQ test, isn't it?
Yeah.
Yeah. Okay, that makes sense.
Yeah. So ANSYS Mechanical,
ANSYS Mechanical, LS Dyna.
Like some of the Abacus solvers, you can run Hexagon's Actran. So these are some of the codes that are suitable to run on these workloads, and there are a bunch of them. Definitely, Seismic is another area where there is a demand for high memory as well as local NVMe. So the local NVMe is actually much more of a requirement for Seismic in addition to the structural codes as well. And that's currently in progress. So we are still evaluating a lot of these codes, and you'll get to hear more about that from us in the future.
Okay, cool. Karthik, thanks for coming and talking to us at reInvent. Hope the rest of the show's good.
Thank you.
Tom.
Here. Thank you.
If you learned something from this talk, then please consider giving us a like and subscribing to the channel so you can find out when more videos like this are available. And if there's an area you'd like to see us go deeper into, don't hesitate to reach out and let us know. See you next time.